Hello, class. Okay, so we're going to talk about one of the ways that heat can flow from one place to another, and this is through a process called conduction. So let's say we have a material that has different temperatures. Like say on the left side, I'm going to call it TH, and on the right side, TC. So that stands for, this is the hotter temperature, this one is the colder. So you can picture, say you're cooking, you have a pot on the stove, and you have a long handle that's maybe made out of metal, and the part of the pot that's on the stove is very hot, but the other end of the bar, so this would be like, say this is the end of the bar that's near the stove, near the burner. So this is very hot, but the end of the bar is cold. Now pots usually have like an insulating handle. Some of them don't. They're just like really thin and hollow, so they can dissipate heat quickly, and they actually stay relatively cool. But what happens is if you have one end that's at a higher temperature than the other, energy is going to flow from hot to cold. So a certain amount of heat is going to flow from the hot end to the cold end. And the effect of that, of course, heat is leaving the hot end, that's going to cool this off. It's being delivered to the colder end, that's going to heat it up. And eventually, if they're just at these different temperatures, heat's going to flow, and eventually this end will cool off, this one will warm up, and they'll reach some equilibrium. But if you had, like, say, this end applied, if you're constantly adding heat to this end, then it'll maintain this constant flow of heat from hot to cold. And the temperature in between these two ends, that's going to vary as well. So like say this is 100 degrees Celsius and this is 0. So like you have a pot of boiling water, and so like the end of the pot is connected to the handle. So maybe this end's at 100 degrees Celsius, that is at room temperature. And maybe we can just maintain these conditions. This end's always in contact with the water, it's going to remain at that temperature, and say the energy is being dissipated on this end. So these two temperatures are fixed, and then the temperature would range from 100 to, say, 25 on this end. We're going to see it would actually kind of vary in a linear way in a situation like this. But we want to know, like, how much heat is going to flow from one end to the other. What factors are going to determine this? And I'm going to write it down. You can say the amount of heat that flows if we maintain these two temperatures. So nothing is changing here. Then the amount of heat is going to be proportional to time. Like say if a certain number of joules flows through this object in 1 minute, if we have the same conditions, in the next minute the same amount of heat is going to flow. So we can say that the amount of heat is proportional to time. Another factor is the difference in temperature, which I'm just going to write like this, TH minus TC. So that's one way of writing it. And this, if you do like the hot minus cold, that guarantees a positive delta T. So, like if these were at the same temperature, TH minus TC, well, there'd be no point in labeling them this way. But if that's 0, no heat is going to flow from one end to the other. And so we did 0 there. But the greater the temperature difference, the more heat is going to flow. Let's say that this is a three-dimensional object. Let's give it a little make it look a little more three-dimensional. Now the heat is flowing strictly from hot to cold. And we have a nice rectangular object. It's just going straight line. And so perpendicular to that direction of flow, we have a cross-section area. And I'm going to say that the heat is proportional to the area. And that should be kind of obvious. Like say you have one bar with a cross-section area A. And in a certain amount of time, a certain amount of heat is going to flow through this bar. If you have another one with the same cross-section area, you get the same amount of heat flowing through this one. And, taken together, we have twice as much area, twice as much heat. And so this should be fairly clear that Q is proportional to the area. The amount of heat flow proportional to the area. And we're going to say L is the dimension where we're following the heat flow. And the longer it is, the longer it's going to take the heat to flow. So the amount of heat that flows through the bar is going to be inversely proportional to the length. And so we can put all this together. So I'm going to write it like this. I'm going to write it as, so we have A, TH minus TC, I'm writing as delta T. We took care of those two. And time, inversely proportional to length. And if we divide by T, then on the left side we'll have power is proportional to A delta T over L. And to turn this into an equation, we introduce a constant, and that constant is called the thermal conductivity. So I'm actually going to write it, leave a little room here. So if we divide by T, we have power is proportional to A delta T over L. Now to turn this into an equation, we introduce a constant, which is the symbol K, letter K, and that's called the thermal conductivity, and that depends on the material. I mean, obviously, the rate that heat flows should be different for different materials. You have, like, say, metal versus wood. Heat flows much more quickly through metal than it does through something like wood or plastic. And so K is a property of the material, and we can write it, I don't want to write it on our equation board just yet. Let's write it here. And this would be fine to leave it this way, but I'm actually going to write it a little differently. So if we multiply the top and the bottom by 1 over K, it cancels out here, and then on the bottom we have L over K. And that's the final form I want to write this, and there's a good reason to write it this way instead of this way. Okay, because we're looking at a particular situation where we have just heat flowing through a material from, where there's a difference in temperature on either side. And I actually, before moving on, I want to work out an example of this. So I picked one up from a book. It's kind of a standard example. But let's say we have the wall of a house. So this is a wall. It's a wooden wall. Let me read this. It's get the. So it's 19 millimeters 19 millimeter thick layer of plywood. And the area of the wall is 35 square meters. Now, plywood, I have to look up the, is 0.08. Now, the units for K, well, let's see, it's joules over, or let's say watts over meter Celsius degree. We could write joules, and then on the bottom, seconds times meters times Celsius degree. But a joule over a second is a watt, so let's just write it like that. Okay, now we've got the plywood. Now the temperature inside the house is 25 degrees Celsius. I'm going to move this over a little bit. Okay, that's just standard room temperature. That's what you want inside the house. It's cold outside though. Outside the house is 4 degrees. And so there's a temperature difference. And so energy is going to flow from hot to cold. And it's going to go through this wall if it needs to. And we want to know how much heat is going to flow out of this house in 1 hour. So let's say T is 1 hour. And so this is something where we simply plug it in. So we have power is Q over T. So let's multiply by T again to get Q. So we have A times delta T Okay. And it's simply a matter of plugging things in. So the area, this is 35 meters squared. Let's see. I'm going to write it like this. The length is 19 millimeters. So we've got L over K. So I'm going to put the K back on top. That'd be 0.08 watts over meters Celsius degree. So we took care of A, L, and K. Now delta T, that'd be 21 Celsius degrees. And finally, time, 1 hour is 3,600 seconds. So like 1 hour is 60 minutes. Each minute is 60 seconds. So 60 times 60, 3,600. Okay, we need another conversion factor here. I'll make this a little, there we go. I'm going to throw in a conversion factor here. There's 1,000 millimeters in 1 meter. So let's just check the units first. We should get joules. So actually I'm going to put in one more conversion factor. A watt is a joule per second. So let's see if this works out now. Let's just go across the top. We have meters squared. I'll write that meter times a watt times a Celsius degree times a second, and then times a millimeter and a joule. So that's what we get across the numerator. On the denominator we have a millimeter, a meter, Celsius degree, and then a meter here, and then a watt and a second, and we can see everything crosses off except for joules. So the amount of energy, so I get the numbers now. We have 35. I'm going to write 0.08 as 8 over 100. So we took care of 35, 19, 0.08. I like writing it that way. 21. And then the rest of this I'm going to write as 3.6 times 10 to the 6. So here we have 3,600. That's 3.6 times 10 to the third, and then times 10 to the third. So let's just multiply across. We're going to multiply basically the numbers. So on top we have 35 times 8 times 21 times 3.6. So here we have 21,168 times 10 to the 6 on top. So double check that. That looks good. And then on the bottom we have 1,900. So I'm just going to take this number and divide by 1,900, which is 11.14. So we have 11.14 times 10 to the 6, or 1.14 times 10 to the 7. I'll just say 1.1. So in 1 hour, basically we have 11 megajoules leaving this room. Now a joule is not a very large unit of energy. It's basically applying a force of 1 Newton through a distance of 1 meter. A Newton is not very much of a force, less than a pound. So, but still, that's 11 million joules. That's a significant amount of heat that's leaving the house every hour. Let's write this down. What you're going to write down is Q1, 1.1 times 10 to the 7th joules. Okay. So again, now that energy has to be replaced. If that energy leaves the inside of the room and goes outside, what's happened is the inside of the room is going to cool off. But we want to maintain this temperature, so we have to keep on supplying energy to keep the interior of the house heated. And we don't want heat to escape. So we can improve the situation by adding a layer of insulation. So we have the same wall as before, but now we're going to add a layer of insulation. And if we're going to do this, we want to kind of see what effect this insulation is going to have. So let's say we wait for 1 hour, see how much energy leaves the house in this case, or at least leaves through this particular wall. It's leaving everywhere it can. So we want to insulate it very well. And see if it's worth it to add this layer of insulation. How much energy is this going to save us? So we have to learn how to deal with this situation. But before, let's say what we've been talking about, let's call this L1. That's the thickness of the wall itself. And let's say the thickness of the insulation is L2, which, look up this example. This is 76 millimeters. I'm going to write it like this. So L2 is 76 millimeters. So the insulation is much thicker than the wall. And let's say that this is K1. Which is 0.08. So K2 is the thermal conductivity of the insulation. this here. And let's say Q2 is the amount of heat that's going to escape now that we have this layer of insulation in place. Okay, so we have to understand, how this works, because we have a formula here, but we can't simply plug this in, because we have, power is A delta T over this, L over K, and the area is going to be the same for both. We have the cross section of a wall. The insulation completely covers the wall, so A is fine. We have a difference in temperature delta T. The problem is, what about L and K? We have 2 now. So I'm going to erase this work. I'll just erase, I should have erased that, but I'll erase everything else. Okay, so heat is still going to flow hot to cold. And we're going to look at it like going through each piece. So let's say P1 is the rate that energy is flowing through the insulation. Sorry, let's call that P2 because of the way we labeled these things. And yeah, so P2 is the rate that energy is flowing through the insulation, and P1 is the rate that energy is flowing through the wall. And what I'm going to state here is that P1 equals P2. Why is that? Well, let's say that was not the case. Maybe you would think that, so again, I'm going to use a different color here because what I'm going to write down is wrong. So let's say you assume, well, the insulator, this insulation has a lower conductivity, so heat should flow through at a lower rate. That might sound reasonable. So maybe you'll say that P2 is less than P1. But what would happen if that was the case? So let's say we look at a certain time interval where 100 joules flows through the insulation, just the layer of insulation. And if P1 is greater than that, that means 100 joules flows through the insulation, but more than 100 joules flows through the wood. And so what the effect of that would be is that if we look at this boundary between the two, it means that energy is flowing away from the boundary, towards the outside faster than energy is being delivered to it. And so if P1 was greater than P2, energy is moving away from this boundary faster than energy is being delivered to it, that means that the boundary itself would be losing energy. And as a result, the temperature would decrease. So if the temperature decreases, let's say TB is the temperature of the boundary. Now, if the temperature decreases, that means it's getting closer to this 4 degrees Celsius, so P1 would decrease. And if this temperature decreased, if it gets lower, we don't know what this boundary temperature is, but if we decrease it, that means that this delta T here would increase. And so P1 would decrease, as if the temperature at the boundary lowered, P1 would decrease, and P2 would increase. And so the effect is that this boundary temperature would warm up. And we could apply the other way if we just reverse this inequality. So if it was the case somehow that P1 was greater than P2, then the effect would be that this boundary temperature would decrease, which would increase P1 and lower P2. All right, I got that backwards. Sorry, if this temperature decreases, P1 would lower, P2 would increase. And so if that happened, these two would become closer. They'd be, coming together. And this temperature would continue to change, and these values would keep getting closer to each other until eventually these rates would be equal to each other. And so even if it was the case that P1 was not equal to P2, if you wait around, if you leave these conditions fixed, and you just wait, eventually it's going to happen that these two will be equal to each other. So we looked at the case if P1 is greater than P2, then this would decrease, which lowers P1, raises P2. And so this value is going down, this value is going up. Eventually, they're going to meet. And when that happens, then this boundary temperature is going to be fixed because energy is being delivered to the boundary at the same rate that energy is leaving the boundary. And so now it's in equilibrium. And so this equilibrium is going to happen in a matter of time. So if we're not in a condition of equilibrium, then we will, as long as we keep the boundary conditions fixed, we will reach equilibrium. So let's say that happened. We're in equilibrium. So P1 equals P2. So let's write that down. So we have A times delta T. Now delta T in this case, I'm kind of using this convention that delta T is T hot minus T cold. And we know that this boundary temperature is going to be between 4 and 25. It's got to be somewhere in between. We're going to go from hotter, the temperature is going to decrease and decrease. Eventually it's going to reach 4 at the other side, but it's going to be like a steady decrease as you go down the layer. So delta T on the left side, I'm going to say it's 25 minus this boundary temperature. And then we divide by L2 over K2. And that equals P2. Oh, I got this completely backwards. I'm looking at it from left to right, but P1 is here, so let me just rewrite that. P1 is A. But now for delta T, this is the hotter temperature. So we're going to say TB minus 4 degrees Celsius. And then we divide by L1 over K1. And that's going to equal P2, which is what I wrote down before, or started to. So we go T hot minus T cold. And then we divide by L2 over K2. And so what we can do here is solve for this boundary temperature. And we can cross off the A right away. And we want to get a common denominator. So it's going to be a little bit of algebra. But the idea is once we find this boundary temperature, then we can calculate the rate that energy is flowing through this material. So let's start by finding the boundary temperature. All right, so we can cross off the A. I want to get rid of the, I think, let's multiply both sides of the equation by L1, L2. So let's try that. Because, we have this K1 in the denominator, we can just bring that on top. So if we multiply by L1, L2, the L1 crosses off. So we'll have L2 K1 times TB minus 4 degrees Celsius. Similarly on the right, the L2 is going to cancel out. So we'll have L1, we bring the K2 to the top. Okay, and now if we distribute things, we're going to do a few steps at once. So TB, we have L2K1. And then I'm going to write plus L1K2. So I'm doing a few steps at once. So basically, if we distribute this, we're going to have L2K1TB. That's this piece. Over on this side, we're going to have minus L1K2TB. So if we take that term and move it over here, it's going to be positive. Then we factor the TB out. So this is the L1K2TB. Okay. Now, just want to check the time here. Doing good. Okay, now this term, when we distribute on the left, we'll have L2K1 times 4 degrees Celsius. But that's negative, so let's bring that to the other side. So we have L2K1 times 4 degrees, and then plus L1K2 times 25 Celsius degrees. And so you can see that we can now calculate TB. We know L1, L2, K1, K2. So, yeah, it looks like we have to calculate L1, K2, and L2, K1. Let's do that. L1 times K2. And because I'm running out of space, I'm going to convert these to meters. So, anyways, we have 19 millimeters, L1K2. Sorry, give me 1 second. Sorry about that. I have a relative in Louisiana in like the worst hit area, so I had to check, but everything's fine. Okay, so L1K2. So basically we have 19 times 0.03. Just the number part. Well, 19 times 19 times 3 is 57. So that should be 0.57. And then we want to convert the millimeters to meters. So we have to divide by 1,000. So I believe that we have 5.7 times 10 to the minus 4. And the units, we have L1K2. You know, we had 0.019 meters times 0.03. So the meters cancel. So we have watts per Celsius degree. Okay, so that's L1K2. And now let's calculate L2K1. Okay, so L2, that's 76 millimeters times 0.03. So 76 times 3, let's see, 70 times 3 is 210. What's that, 228. So I think we have 2.28 times 10 to the minus 3 watts per Celsius degree. Yeah, I think that's right. Okay. And so now let's kind of put everything together. So we have this term, L2K1 times 4. That's Celsius degrees, so we're going to get watts. So like both of these terms are going to be in units watts. So L2 times K1. Oh yeah, we've got that already. That's 2.28 times 10 to the negative 3 times 4. So let's see, 2.28 times 4. Let's just do this. We have 9.12. That would be times 10 to the minus 3. We're going to get watts over here after the second term, so I'll just write down the number. And then we're adding this, L1K2, that's 5.7. We'll worry about the 10 to the negative 4 later. Let's do 5.7 times 25. So that's 142.5. I want to get the same exponent though. So that'd be times 10 to the negative 4. So let's see, we want to get the same 10 to the minus 3 exponent. Alright, so this is times 10 to the negative 4. Yeah, so this is let's say 14.25. And then on the bottom, actually I think it'll be easier. Let's divide this by 10. Should have done this earlier. And then multiply this one by 10, just so they get the same exponent. It'll be much easier to add them. So on the bottom we have L1K2 plus L2K1. So we add these. So 0.57 plus 2.28. Let's see, that's going to be units here are watts per Celsius degree. So I think that's 2.85. And all these 10 to the minus 3s are going to cancel out. So I'm just going to cheat and use a calculator. So what I'm getting is 8.2, and the watts cancel out. We have per Celsius degree. So I'm getting this boundary temperature of 8.2 degrees Celsius. Let's see if that is correct. I'm going to check these numbers. Sorry about this. Let me just check these. Should have just done this from the beginning. Yeah, that one is 0.57 times 10 to the negative 3. And then L2K1, 76 times 0.08. Oh, I got that one totally off for some reason. This one was supposed to be 6.08. Not sure what I did there. Okay, sorry about that. So that number is 6.08. So basically, and again, everything is now times 10 to the minus 3. And since I have the book here, yeah, if we just plug these numbers in now, this boundary temperature is 5.8 degrees Celsius. And of course, you always want to check and see if it makes sense. My previous answer was wrong. Forgot what I even had, but it wasn't this. I think it was 8 or something, which was actually seems reasonable, but it has to be between 4 and 25 degrees Celsius. Yeah, just you want to check those limits to make sure that it makes sense. But yeah, it should be 5.8 degrees Celsius for that boundary temperature. Okay. Now, getting all that, it's a lot of work to get through this. And so we're going to see there's actually kind of a better way to do it. But what we're going to do, now we want to answer the question, how much heat is going to flow through this wall in 1 hour? And now that we have this boundary condition, or this boundary temperature, let's get rid of all of this. say P2. Or let's calculate Q2. The amount of heat flowing through the insulation in 1 hour. So we have A times delta T, and now we know what delta T is. So we have 25 minus 5.8, so that would be 19.2 Celsius degrees, and then divided by L2 over K2. And then times 1 hour. So now that we have we need this boundary temperature to calculate delta T. So now that we have that, it's simply a matter of plugging things in. So we have 35 meters squared. And divide by L2, which is 76 millimeters. And then K2 is 0.03. So I write 0.03 as 3 over 100. And, or we can move K up to the top, so that number should be on top. So we got A, L, and K taken care of. Just so I don't forget. 1,000 millimeters, that'll cancel that out. And now we have our 19.2 Celsius degrees. And T again is 3,600 seconds. Now, the units, I'm going to cancel out this way, just cross things off, because we're doing the exact same calculation as before. So meters squared, there's meter and there's a meter, millimeters, Celsius degrees. And what we have left is a watt times a second, which is a joule. So we have a joule per second times a second. So Q2 is 35 times 3. I'm going to leave this for a moment. Times 19.2. And then times 3.6 times 10 to the 6. So here we have 3.6 times 10 to the third, and combine it with that 10 to the third. And on the bottom we have 7,600. So let's calculate this number here. Okay, 35 times 3 times 19.2 times 3.6. If you do all that, you get 7,257.6. And then let's divide by 7,600. This is 0.95 times 10 to the 6 joules. Where what we had before without the insulation, if we write it in the same units, so here we have Q with insulation is 0.95 times 10 to the 6 joules. And then Q with just the plywood with no insulation, this would be 110 times 10 to the 6 joules. And so just with the same exponent, we're looking at this factor, we're comparing 0.95 to 110. So in 1 hour, without insulation, we'd have 110 megajoules, or 110 million joules leave through that wall. With insulation, we have roughly 1 megajoule. So that's a factor of 110 improvement. So that greatly reduces our energy cost and prevents us from wasting energy. So insulation, very, very useful, obviously. Okay, now that was kind of a lot of work, and there's a nice way to bypass the this we had to find this boundary temperature first, but there's a way we can kind of bypass that. But actually, before I get to that, we calculated Q2, like the amount of heat in 1 hour that's going to pass through the insulation. And we could have just as well calculated Q1, or the amount of heat that passes through wood in 1 hour, using this difference in temperature and this value for L and this value for K, and we would have gotten the exact same number. Because remember, P1 equals P2. So energy is flowing through each material, the wood and the insulation, at the exact same rate when we're in equilibrium. And so, it's just a preference. You can calculate P1 or P2, and you should get the same answer. So we just did one of them. But if you want to check it, you can plug it in. So instead of 19.2, you'd have 1.8 and then use L2 and K1. L1 and K1. Okay. Now I think, I mentioned there was an easier way, but this video's kind of been going on for a bit. So I think we'll pause here and I'll talk about maybe a simpler way to do this in another video.